That in order to get a convex formulation of an optimization problem, you go to a higher dimension. Okay? Did you all hear that? By increasing the dimension of the variable space, we get a convex program, in fact an LP, while the dynamic program equations is not a convex anything. All right? So, but. So good news, it's convex. And I think that's something that's been missing from practitioners, that this is a really valuable trick because of that. And so if you're going to do some approximation techniques, this could be the way to go. But it just hasn't gotten traction yet. So people don't use this yet, but I suspect they will in the future. And yeah. So D was a number of states. If we have D states and M actions. Yeah. One more comment and then we'll stop. On the other hand, the reinforcement learning community is obsessed with this, which is the Q function. And so they're all trying to approximate a function in this higher dimensional space. And so, if they're doing that, then why not use LPs? Number one. And guess what Q star is? And then we'll stop. In terms of the context here. So I've got a linear program. How is that related to this DP equation? You know what it is?
I know what it is, but
yeah. Oh, what? Don't tell me.
I don't want to blurt it out.
Why not?
I want to see someone else know it.
What do you mean? It sure isn't obvious. Anyway, anybody know?
You mentioned it.
Did I?
Something to do with dual variables.
Okay, so you both remember I said that. So every linear program has a dual, and Q star is a Lagrange multiplier. No. So this is only for each x prime. Well, anyway, Q star, So this is true for every x prime. I think 8 star is the Lagrange multiplier, but then Q star comes. Anyway, it's basically. I'll have to look it up, but it's basically so my point here is about complexity. Is that in computer science, this is the object of interest and it has the same complexity, but it turns out that I'll have to tell you next time. It's a connection with duality. Because it's not precisely the dual because that's x prime, but yeah. All right. Yes.
So when you have gamma, how do you recover the conditional?
Damn! Thank you. Shit. I missed one big thing. Yes, thank you. So we proved that G star the script G is a polyhedron, right? And it's convex and all that stuff. And guess what the corners are? The extreme points. Anybody want to guess? That should be in this proposition. Bonus material. What is this? There's going to be a finite number of extreme points. I'll label them gamma 1, gamma 2, gamma 3, gamma 58. I don't know. There's going to be corners. And a convex polyhedron is just, every point inside is just a convex combination of the extreme points. So what's an extreme point? These are deterministic. So it's the set of gamma such that this phi becomes degenerate. Isn't that beautiful? So you're able to prove that the optimal policy is determinate, without lots of generalities, deterministic. I mean, of course it's possible. We're trying to minimize. So a typical thing is like that. That's C. This is a polyhedron. And that is gamma star. All right? All right. But it could be that it's parallel with a face, in which case it's more than one optimal policy. Yeah. But anyway, without loss of generality, for a linear program, you can restrict to extreme points, and extreme points exactly deterministic policies. Good old man. It was a beautiful result. Yeah. Thank you. I forgot to say that. And yeah, you get it by decomposition, right? Once you know gamma, you've got your policy. Yeah.
So you still need to go like with pi, but pi is...
Oh, no, yeah, no, you divide. So given gamma star, you find the marginal, and to get the policy, this is division. Yeah, you take gamma and divide by pi. Yeah, so 2 steps. But yeah, maybe that wasn't your question, but this was really important. Yeah. But now we're definitely out of time. So, yeah.